This video is made up of all of the top tips I've found most help my students. What I've actually done is over many years written down and made notes after every tutorial, and this is just me compressing the best examples into a very quick video. This first page is very wordy, but trust me, have a look. Look, it's all going to be diagrams and stuff after this page, so bear with me. I think maybe some of these are the most useful though, even though all the other stuff maybe will feel more useful to you, depending on how you think. Anyway, let's get on with this. Remember that mechanics questions are often very difficult to get started with because you have to understand the situation, draw pictures, make equations, but then once you got started, I find that to compensate, the exam boards usually make the question quite easy to finish, the maths quite easy to do. Remember that? So if you're struggling with getting started in a question, probably everyone else is as well, it's fine, it's kind of how it's supposed to work. Always be on the lookout for something changing partway through a question. Seems to be very common in mechanics, perhaps something that was stationary is suddenly moving. F equals ma. This is just incredibly common. Remember that only applies for constant acceleration. If a equals 0, is that constant acceleration? Yeah, it is. It's constant. It just happens to be 0. In which case F would be 0, so all the forces are up to 0. Be on the lookout for 2 or more topics being combined into one question. I've seen a lot of students struggle with the question because they don't notice. They spot the first topic, but they don't notice the second topic, which is where they get stuck. Finally, and this is probably the most useful thing I tell to all my students in terms of, and this is what they tell me this is most useful, and I see it's the most useful in how they then perform, is the question looking for 2 answers, then find 2 equations and solve them simultaneously. What if it's looking for 3 answers? Well, then find 3 equations and solve them simultaneously, which is kind of less common. What if it just wants 1 answer? Then you probably just need 1 equation. Okay. Remember the area under a velocity time graph is the change in position. Remember the area under an acceleration time graph is the change in velocity. The normal reaction force is perpendicular, that word says perpendicular, to the surface. That's it, nothing else is important, it's perpendicular to the surface. That word there says physics. Mu is a rough approximation of complicated physics. Why am I saying this? A lot of people question it. Well, not a lot, but some people with really good intuition, because it doesn't really make sense. I would say, having done a physics degree, in my opinion, it's one of the worst models in physics is this. Mu times the normal reaction is a terrible model, I think, for friction. And if you go into advanced level physics, they're always using like computer models or much more complicated models for friction. But hey, it'll do if that's what you've been told to use. And it's okay-ish, maybe. Is something at rest? Okay, let's say it is at rest. Then we don't know where it is. Remember that. We haven't been told anything about the position. Maybe we are somewhere else, but if it's at rest, and that's all we know, we don't know where it is. What we do know is it has 0 speed, okay? What about its acceleration? Do you know what? We don't know. Maybe it's only instantaneously at rest. It could be accelerating, but just at this moment in time, the speed is 0. Okay, I kind of use 2 main ways to add vectors. The first one is I just kind of draw them top to tail, like so. Then the resultant finishes off the triangle. In this case, I could use cosine rule to work it out. An alternative, and this is my personal favourite method. You can also break it into components. Maybe in this case we've done vertical and horizontal. In which case you can then you can see where the resultant will be, and in this case you'd use Pythagoras to work out what the resultant was. And remember, you can use tan to the -1 to then work out the angle. Why must the ball Q be moving to the right after the collision? I quite like this, a bit of a logic puzzle. It's a good extended thing into how to think about things like this. Let's look at 2 scenarios. Scenario 1 and scenario 2. In scenario, right, first of all, before I do that, can you see that the total momentum at the moment is to the right, which means afterwards the total momentum must be to the right. So one of them has to be moving to the right. So in scenario 1, maybe Q is moving to the right, in which case Q is moving to the right. So that's sorted that out. In scenario 2, let's say P is moving to the right. Well, if P is moving to the right, it can't have like magically phased through ball Q in order to get past it. Ball P must be here, and ball Q must be further to the right and must also be moving to the right. So therefore, if P is moving to the right, Q is also moving to the right. Ergo, we have shown that Q must be moving to the right. Another little practice thing I like to do, which I think sort of draws attention to lots of things. Let's draw all the forces on this plank. It's going to be trying to kind of fall down. So, well, not so. There's a normal reaction here because it's touching the ground. It's going to be trying to fall, so the friction here will be to the right. Oh, by the way, there'll be a weight. Then there's obviously going to be a normal reaction here, and again, because the plank will be trying to fall, there will then be a friction here. So I make that 5 forces. I've got a trick for how to resolve things into components. My students usually really like this. They've often not heard of it before. And I do it to save time, because they often look at me when we're doing exercises together and go, how'd you do that so fast? It's like, oh, I've got a trick. Okay. Let's imagine it's a really small angle of 10 degrees. I can instantly tell that this component here must be f cos 10. Has to be. Why? Because cos of 0 is 1, which means cos of a small number, and let's say that 10 is a small number, is approximately 1. And that makes sense because the horizontal component here has to be not that much different from the original value because it's not much of an angle. And then you can use a similar argument to show that this vertical component has to be sine, because sine of 0 is 0, and that should be quite small. Oh, here we go. Here's a bunch of top tips for working with SUVAT. I'm going to use a different colour. Let's use blue. Remember that, so I'll just go through them the way I've numbered them on the screen. Remember that at the start, S is often 0. Next of all, so that means S is 0 here, specifically. Careful. I like to draw an arrow with a little plus, just showing which direction is going to be positive. So in this case, I'd probably put positive up here, because then I could have acceleration due to gravity being in that direction and being negative. Anyway, but I'd be careful I probably wouldn't draw that on. That would just be implied from the fact that I'd drawn this arrow with the plus, meaning that gravity going down is negative. Anyway, at the top, remember the velocity will be 0. Another thing is, remember that this side is symmetrical to this side. Why is that? It just is. Okay, maybe that'll do for you. One of the reasons is SUVAT kind of assumes no friction, which means you are the maths kind of comes out as, oh, well, it's going to do exactly the same curve on the way back. Anyway, at this point here, S is negative, by the way, because it's already dropped below S being less than 0. But be careful, V is not equal to 0. Why? Because it's falling. Yeah, it's falling. There you go. So it's it's not gonna have 0 velocity. You might be thinking, but wait, it's on the ground. If it's on the ground, it has 0 velocity. No, because we're going to be talking about that moment in time just before it touches the ground. Why? Because SUVAT is constant acceleration. And once it starts to make contact with the ground, there's an additional force on it, which means it's no longer constant acceleration. Okay. What else we got? Oh yeah, remember that if you end up with a negative t, like, I don't know, negative 0.5 or something seconds as your answer, that means you're looking at a moment from before this started, which may well not be what you're after. Okay, so there's some of my thoughts about that. Oh wait, hang on, one more. This is my thing that I often see examiners do. You've actually got vertical components and horizontal components, and you can do them separately. So they may set up some crafty little question in the exam where you can make both of those into meaning you've got two equations, you've got simultaneous equations, so you can find two unknowns. Do you remember what we said at the very start of this video? What if, yeah, okay. Oh, here's just a couple of common-ish equations which you might see, and I find them quite confusing. I know a lot of my students find them confusing. P equals Fv. This is work done, so power is force generated times the velocity travelled at. Work is force times distance. It's like, wait, what? Is that the same thing? Because they both say work? I don't really understand. Just, if you look at it carefully, notice that this is just energy. But this one here, that's energy per second. Whoa, my pen's going weird. Because velocity is meters per second. So this per second here, that's where the per second comes from. So that's the difference. I won't go on about that anymore, but remember that's the key difference when you start working with those two equations. This is another thing I'm not going to go on about too much. This can extend into lots and lots of detail, but what I would say is, depending on, say you're doing some exams, you might want to remember this equation. It might be very important. Remember that if E equals 1 is an elastic equation, because that way, because this is telling us that the difference in the velocity stays the same. But if E equals 0, what does that actually mean? Well, that means that you've got a fraction which is equal to 0. So something over something equals 0, which means the top is 0. So that means that v2 minus v1 equals 0, which basically means the velocity is going to be the same. So maybe the things will stick together or whatever. In case you have to cover this, differentiation or calculus. Hopefully you're learning calculus from somewhere else if you're then having to use it here. So here's just some basics. ds dt, that's velocity. d2s dt squared, that's acceleration. dv dt, that's also acceleration, kind of obviously. In case you're wondering, may or may not have covered this, the differential of acceleration with respect to time is called jerk. And the human body can only take so rapid a change in acceleration. So the human body doesn't like high acceleration, but it also doesn't like the acceleration to change too quickly. So if you're designing things like aeroplanes or fairground rides, you've got to make sure the jerk isn't too high, or that can damage the bodies of the people riding. Penultimate page. Oh, do you remember? I think I might have said earlier that something was the most useful thing my students ever hear. This is often the second most useful thing. Change is the value after minus the value before. Maybe that's really obvious to you. It's not obvious to me, because I'm just like, well, I think this is kind of arbitrary. Well, let's say it is arbitrary. This is what was decided. This is a convention. Change is value after minus value before. Remember, joules is energy and newtons is force. Sometimes you'll see the phrase, sometimes momentum is not conserved. Well, what does that mean? That means external forces may be applied. Well, because then that means momentum isn't conserved. And I'm just like, does that really mean that? Because if there's an external force, then momentum's still conserved if you take into account where that force is coming from. Well, don't shoot the messenger. This I hear a lot of people say, sometimes momentum is not conserved, and this seems to be what they mean by it. So now you know what to say to keep them happy. What else have we got? Oh, this is the last page. Yes, I like to we've kind of covered this already, but I like to cover this again because I think it's so important. Let's add up all the forces on a body. What if all the forces add up to 0? Then it's at rest. All careful, or it's at constant velocity. What if all the forces don't add up to 0? Okay, so then it's accelerating. And we're going to kind of assume that it's constant acceleration, yeah? So either the force has constant magnitude and is always perpendicular to the velocity, in which case it's moving in a circle. Otherwise, all we can say is it's not moving in a circle. There we go. Hopefully that was helpful. Just a barrage of things which I find my students find useful. This is just kind of, yeah. Good luck with your mechanics.